you realize that you came to them. So we're going to wrap those up today and make sure that you understand the conclusions you actually came to. So first of all, we'll come back to that momentarily. Last project, decent? Fair? Understandable? Good. Last quiz? Okay? Pretty straightforward. Nothing crazy. Just basically running to normal. The idea of your last couple exams, so you have your out-of-class exams already posted. Hopefully you guys have got the chance to play with that. If you haven't, don't worry. You've got time, obviously. Your exam isn't until next Thursday, I don't think. And that's when that one's due as well. Just realize there's an Excel component to that. And one student in the other 243 who's gotten into it and started using it, it misbehaved for her, and she had to change computers to have it work. That happens about 1 in 100 cases, I've noticed, that the Excel sheet, and I don't know why, and IT can't figure out why. So there's some kind of a weird glitch. So basically the big idea, we'll come back to this today when we actually start talking about the central limit theorem in more detail. You'll know if something's wrong right away, and I'll show you how you'll know. If that makes sense. Maybe it doesn't make sense yet. You will. It will make sense. Yeah, Megan, it's okay. It will make sense later. So basically what I'm saying is don't wait until Wednesday night to start that. Because if you're the lucky 1 in 100, you're going to have to move computers. And at 2 in the morning, that might not be easy to do. So just give yourself time. It won't take you long to do what you have to do with that spreadsheet. It won't take you not even 5 minutes. But it might take, if you wait till 2 in the morning to try it, it might take you 5.5 hours to put it on the computer to try it on. So I'm just saying, I got, so just the last 244 project, which was due at 8:15 this morning, I was sitting at my desk, drinking my last bit of my cup of coffee, and I heard bing, 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 at 8:10 or 8:14, 5 or 6 of them came in. So I can't answer your question, except saying that it happens. I don't know why, it just happens. I don't know. I don't know what that is. So anyway, just realize, it's kind of like when a rear main seal fails on a car. It's a 15-cent part, that's $2,000 in labor to replace. So running that spreadsheet's a 5-minute F9 push. But you got to make sure the computer's ready to do that. And that's what you don't want until the last minute to find out. So anyway, we'll come back to that. This central limit theorem idea, which we're going to talk about today, since we're going to finish it up today, I don't want to have it on the in-class part of the exam next week. And the reason is simple. Usually when we finish up something in class, the next class we take questions if you guys have questions on it. We don't get that because this is our last class together. So I saved all the central limit theorem stuff for the out-of-class exam, so you've got plenty of time, if need be, to email me back and forth about stuff you'll get stuck on. I don't think you'll get stuck because the exam walks you through pretty well what you have to do. But if you do get stuck, you can email back and forth. You can look at the homeworks that are posted for central limit theorem, which will answer quite a few of your questions most likely, or just email me. But I don't want to be timing you on an exam on something we didn't have a chance to discuss as a class. Does that make sense? It just seems unfair. So the in-class exam will just have binomial and normal on it. Binomial and normal. And I've got 2 examples in each for the stuff that I've actually experienced in walking around and observing things. Please.
So is the final going to be like 5 questions like all the other ones? Ish? Or is this going to be...
I think so. Well, it's 4 questions. But there's 2 binomials and 2 normals, and I broke them into parts so I don't have like 4 15-point questions, because then people feel threatened. They're like, oh my god, if I didn't get it perfect, I'm going to lose everything.
Sure we weren't going to walk into 30 questions.
Oh, no. I think what I'm shooting for is probably 10 5-point questions. Okay. Like the other ones kind of are. I mean, it's basically that every single time. When you put them both together, it's like 20 questions, 10 in class and 10 outside. It'll be just like a 3rd exam. It's not cumulative, so it doesn't go all the way back to day 1. It just comes from the last exam up to this. So, cool? So you're not going to walk into like some crazy multiple choice exam or anything like that. So, and your out of class has, I think, all 3 sections on it too, I'm pretty sure. It's got a chicken example, chicken salmonella and chickens, so that's binomial. Then you've got a normal distribution problem, which you'll know because you see the word normal distribution. It's the airline seats, which is like your like that homework problem whatever last time with the shower heads in the bishop. I finally went back yesterday. I finally found a block of time and I recorded videos for that normal distribution homework. I had a couple in there, so that if you need those are there now.
Where are they?
On the homework sheet itself.
On the homework
so
sheet.
If you click, there's a couple links. There's not many, there's only a couple, because most of them already had solutions.
Right.
But I put an E1 video to get you started on that one we did in class. Right. And then I linked off the one in the book that didn't have a solution. So at least you have a starter for those now. What else? I think that's it. My God, that's all that's left. Yay. Well, that, make sure you guys understand what the hell we did yesterday, which is what I wanted to do today. Just get in there. You don't remember, that's okay.
I didn't write anything down, I don't remember.
That's well, and you don't really have to, because this is the only lesson I've got where the entire thing is contained in a spread, in a PowerPoint. I try to avoid those, but this one's so nice because everything's wrapped up in a PowerPoint and an Excel spreadsheet. And honestly, well, you did write stuff down. It was that in-class quiz you turned in. But unfortunately, because it's at the end of the class, Amber won't pick it up until today, which means you won't get it back until Thursday, essentially. So this is why I want to wrap up today and make sure you guys knew what you came up with. So let's recap. Any questions you guys have before we recap? Anything bothering you right now? The cold. Okay, I can't do a whole lot about that. I'm sorry. Okay. Anything statistical that I can rest your mind about? Not the cold. That's actually statistical. I can't. I sent you guys a link. Speaking of that, I just sent you guys a link. It's called. Oh crap! I forgot what it's called. But it's basically it takes news headlines and then it writes them in a statistically literal way. So in other words, my buddy Dave, who's working on his PhD down in Columbia, sent this to me. The headline was, unemployment rate jumps from 7.6% to 7.8%. Now, good. Robert laughs, Michael laughs as well. And it's funny, because this is the kind of headline you see all the time. So that's the headline, ripped from the news. The mathematically literate interpretation of that is, unemployment rate's probably just under 8%, but we really can't tell what it's doing. And this becomes a 244-ish kind of joke, because a jump from 7.6 to 7.8% is meaningless. It's kind of like when they say, oh boy, Obama's finally in the red. Now more than half of people disapprove of what he's doing, because he's at 52%, with a 3% margin of error. Exactly, JC. And then you say, wait, can you actually, no, you can't tell anything from that. But the headline says it. Another headline was, average football player makes, I think it was $4 million per year and lasts 4 years in the NFL. Truth, average football player makes $0 per year and lasts 4 years in high school.
I was going to say.
But that's the thing. That's the kind of statistically illiterate crap that comes across headlines all the time. And so I sent you the link to the website if you need some time to just stop. What's that, Robert?
I said it sounds great.
Oh, it's fantastic. It's just a whole page of those. And the guy has a little whiteboard that he draws pictures on. It's fantastic. It's fantastic. So I said it to you, if you need a study break, just scroll through that. Still be doing statistics. Which we get a laugh out of too. So, anyway. What the hell were we doing last time? As in 48 hours ago, which was a long time, I know, and a lot of cold between then and now.
Like correlating everybody's data from the dice.
Perfect! We were rolling these dice and then correlating data, and we had a board full of beautiful graphs. So the distributions that you guys were rolling from, there was the blue groups. Where are my blue groups? My friends that had blue dice last time, there were 2 groups of blue, yes. There were the yellow ones, we had some yellow groups, yes. The green distribution, yes, green. Orange, this is one of my pet faves just because it's a goofy graph. And then the red, which looked bell-shaped already, yeah? Already looked bell-shaped. And we slapped your guys, these are the population distributions. So this is what you actually have in front of you. And we talked about that being a bit fictitious, yes? A bit fictitious. It's kind of like the unemployment rate, jumps from 7.6 to 7.8. The reason that there's any uncertainty at all in the unemployment rate is because the unemployment rate is based on a what? What do they do to get those numbers?
Oh, they're used unemployment.
But how, in what way? Go back even further. You're right, unemployment. Once they've defined what unemployed is,
right.
What do they have to do?
I think they call the people that are unemployed and they ask them if they're looking for work.
Good.
How long it's been since they've looked for work.
Good. Do they call every single unemployed person?
No.
So they draw a what? They draw a sample. Yes, no, Robert, what you're giving me is the process. Thank you, it's perfect. But the trick is, you can't ask every single person because there's too many of them, so they draw a sample. And every time you draw a sample, what happens? To the next time you do the exact same, suppose you're trying to get the unemployment rate at the same time, today and then later on today, and you call different people, what's going to happen to the rate?
Well, it's going to vary.
It's going to be a little bit different, isn't it?
Yeah.
So the unemployment rate jumping from 7.6 to 7.8
You just called one.
could just be random chance. It could have also gone down in the next survey, right? That's why I had you guys correlate all your data, to get a more complete image of what's going on. Because even with collated data, you're still never going to know what these things are. Because you can't see the whole population. The only way to get these values is to get the whole population. That's why when the guy at High Desert Ranch Home says, 90% of the time, we ID these chicks correctly. And I go, okay, I'm going to call that mu, because I have I don't know what you're talking about. I'm assuming your process has been done millions and millions and millions of times, or hundreds of thousands or tens of thousands of times, so that even if there is a little bit of fluctuation from the 90%, it's so close I can call it 90. So that's different. That's been replicated so many times that I don't doubt it anymore. But in a normal sized sample, you have to allow for error in the measurement, which is why I had you guys collate your data and slap them on the board. Now, what do you remember? What do you remember about the graphs we put on the board on Tuesday? Oh, they were all bell curves. That was surprising, yes? That was surprising. Why was that surprising?
Because our original one weren't.
Because most of it, with the exception of the red one, yes, very nice, Kate, with the exception of the red one, which was already a bell curve. The other distributions weren't bell-shaped at all. So, for example, why would the blue one turn into a bell curve?
Because the probability of getting a 2 and a 3 is very low, and then getting 2 and a 3 in a group of 4 is even lower.
You hear that? The trick, the extremes, the ones that are highly unlikely, are going to be very, very hard to get. And add to that the fact that it's very hard to get a sum of 2 anyway. It's easier to get a sum of 7 because there are more possibilities of getting 7s. Even on these unfair dice, for the most part, it was easier to get 7s, except for some. Orange was not like that. But to get the extremes once is rare enough, and then getting them multiple times, Hattie, is exponentially harder. JC, go. What were you going to say? I didn't hear what I heard you say sample, but then I didn't catch the rest. Oh, damn.
Our sample was, okay, so we're talking about the bell curve.
Yes, ma'am.
Of the population. So if we just take a sample of that, it will reflect in the population, but we still have.
Yes. How? Yes. So one thing just got said. They're all bell curves. That was the first thing. It was kind of like, bing, whoa, that's cool. What was the second thing that was cool, JC? How did the bell curve reflect the population? Not in the shape of the distribution, but what did the bell curve point to? Yes, it pointed to the average. The hump on the bell curve humped where the average in the population is. Now some of you are like, yeah, but we already knew the average in the population. And we did for our dice. Do you know the average in your population in general? For example, the average number of unemployed people right now, to the exact person right now at this moment. No, you don't know that, do you? You don't know that. But if you draw a sample, what this tells us is we'll get a bell curve in our sampling distribution, and the high point of that bell curve is going to be pointing to the sample-ish. Pointing-ish, big-ish on this one. Because there is wiggle back and forth. We'll come back to that. We have to account for that. Kate, go.
The reason, well, because of that is because your sample size is still going to represent the frequencies of how often your stuff is going to happen.
Yes.
So there is the wiggle room, but
Good.
for those things, the frequencies doesn't change.
Now, let's tie into that now. Thank you. Perfect segue. Thank you, by the way. Watch this. What I'm going to do is I'm going to replicate the study we did yesterday. So first off, here are the blue dice. Now, I'm doing this on just the blue dice for a couple reasons. Number one, I could do it on all 4 sets, but it gets a little overbearing, plus it looks like a Skittles bag up here. It looks a little ridiculous. So just if I stick with one set of dice, you'll see what I'm getting you to see. And it applies to all the other colors as well. It actually applies to any distribution of any numbers. But since you were just playing with this one, I figure, what the hell. So this is what the blue dice would look like if you blew them out and looked at all the sides on them. Okay, we know the average is that with the standard deviation of that from yesterday. Okay, I put WLOG for without loss of generality. That means this will apply to all possible dice, all possible populations that we're sampling from. Fair enough? First up, I'm going to click over to here, shrink this down so you can see. Now what I've done here is I've rolled these dice, quote unquote, rolled these dice 4,000 times. So you guys rolled them 100 times, right? Total. Rolled them 100 times, broke them into groups of 4 and did the averaging. This graph right here represents 4,000 rolls of the dice. Here are the sums over here. 12, 9, 10, 11, 11, 11, 4, 4, 7, 2. There's a 2. Pretty rare, yes? Pretty rare 2. 2, 2. Right. Every time I press F9, it rolls them again. Now, does that graph look familiar to you guys? Does that graph look familiar to you guys? It might not from yesterday, but let me back up here. There.
It's kind of like the original.
That's the original population graph, yes? This is the original population graph. Okay, so far, that's the original population. So I'm hitting F9, I'm hitting F9. Oh, I gotta get the Excel sheet. I'm hitting F9, I'm hitting F9. Notice it's wiggling. This is what Robert and Scott said earlier. If I do a survey and then do a survey immediately later, I'm going to get slightly different results. But I'm never going to vary too far from where it should be in reality because of the randomness of the number draw. JC?
Isn't that good to have like the wiggle room?
You have to.
Because things aren't gonna be the same for
Mhm.
everything.
And if they are, you know what happens?
Analyzing.
The one-armed man chases Harrison Ford and tries to kill him. That was the premise of the movie The Fugitive. Do you remember? Do you remember the movie The Fugitive? I'm going back in time about 20 years now. The whole point of that movie was Harrison Ford figured out the liver slides looked too good. There wasn't enough variation in them. And they sent the guy with one arm to go kill him. Remember?
Yeah.
I'm giving it away. I apologize if you haven't seen the movie yet. But that was the whole point. So unless you want to kill Harrison Ford, you best have some wiggle room in your dating. Now, thank you, JC. I'm not trying to trivialize what you're saying, but you're 100% correct. If you don't have that wiggle, something's too perfect. It's interesting you bring this up. In 244, just yesterday and the day before, we did something called goodness of fit testing, which is assuming, and the last experiment we did in class, we cracked a bunch of bags of M&Ms open and counted how many colors we got, and then compared the colors to what Mars says the colors should be. If the colors we got were perfectly matched to Mars, I always tell them the same thing, I like my shoes. And they never are, because assuming there's randomness in the process, they shouldn't be perfectly matched. And the graph that you compare them to indicates that by hitting 0 at 0 deviation. You have to have a little bit of deviation and the graph actually gets higher like a bell curve. But too much deviation and you get too far away from what it should be. And there's this great curve called the chi-square distribution that actually measures that, which we'll get to in 244 at the end. We crack open M&Ms and count them. So, but that's the point, is you have to have a little bit of deviation from the norm because that's natural. It's called sampling error. And it has to happen because we're not getting the whole population. Yeah. Even though I've got 4,000 rolls of dice, that is not the entire population. Not even close. The entire population is infinite. Does that kind of make sense? But if I was to do a cumulative, if I hold down F9 and have this keep counting and keep counting, this would start stabilizing. But just like back, and this probably seems like a year and a half ago when we did Chuck-a-Luck, when I held down F9, that graph basically stabilized. It looked like it stabilized, but it was still varying in very, very small decimal places. So there's always going to be some of that dance. So thank you, JC. Very, very good point. Now, this was the first thing that you did on Tuesday. The next thing you did was you averaged your rolls 4 at a time. So this is the exact same data that we saw on the previous sheet, but now you'll notice, or maybe you don't notice, I'll show you right now. All 4 rolls are now averaged here in this cell right here. So if you roll 8, 11, 8, and 2, that's an average 7, 7 1/4. 10, 7, 7, 11 is 8, 8 3/4. 5, 11, 6, 11 is 8 1/4. 1,000 times. You guys did it 100, this is 1,000. Now take a look at the graph of all those averages. There she is, let her dance. What's happening every time? What's happening?
It's wiggling.
It was wiggling, good, good, thank you for that. It better be wiggling, otherwise Harrison Ford dies. It's got to wiggle, the bell curve. Now sometimes it's not, that's pretty damn perfect. It's not, see? It's a little bit skewed this way. But now, it has to be a little bit skewed. The average is at 8.2-ish, yes? So you'd want the bell curve to have the highest point between 8 and 8.5. And you'd want it to be kind of perfectly balanced off to the sides. But it's got to be a little bit skewed because 8.2 isn't exactly 8.25. It's going to be a little bit to that side, which explains why this side's a smidge higher on average. On average. Now sometimes, notice right now, the highest bar is not where the average is it? The average is at 8.22. The average here looks like it should be at 7.5 to 8, which is a little bit south. But notice, as I keep pressing F9, on average, where is the highest bar? On average, and now I'm using the word average to imply mode. Most often, where is the highest bar? Where that mu actually should be, which is 8.2. So once again, we're coming back to the bell curve telling us, hey, this is fantastic. Where's mu? Mu's at the highest bar, usually. Yeah? Mu's at, and this is what, you're on a class exam, FYI, this is what I was talking about. You're going to be simulating this curve. If you press F9 a bunch of times and you don't see a bell curve, something's wrong with your machine that you're sitting at. Just change the machines and do it again. You should get a bell curve almost immediately on that exam. That's what I'm getting at here. So if you're not seeing a bell curve, something's going on, and I wish I could fix it, but I can't. Kate?
Okay, I might be just overthinking.
That's okay, go ahead.
Go ahead and let me know if I am. Okay, so with your population of 4,000, it's
Yes.
not...
Oh, it's a sample.
Okay, your sample,
It's a
whatever.
big sample.
But
Actually, it's only a
4,000
sample of 4.
Well, no, for the first one.
Yeah, so the sample being was 4. Oh, that sucks.
Yeah, okay. Well, the first one, when it wasn't a bell curve,
Oh, gotcha. The actual population, just not this
Yeah.
one. Yes, go ahead.
it wasn't a bell curve. And then when we did 100, it became a bell curve, and then when you just did 1,000, it became a bell curve. Where is the...
Hold that thought. You're not overthinking, you're pre-thinking.
Okay.
We're going to hit that point last
Okay.
because it's actually the least important because it's the most contentious point of this whole thing.
Okay.
We'll come back to it if you don't mind.
deciding when it becomes a bell curve?
Yes. Now, I want you to understand something, friends. Kate just asked a very important question. She says, okay, so obviously the bell curve kicks in. But when does it kick in? And the answer is it kicks in immediately with a sample of size 2. It's just that the bell curve is going to have certain characteristics that we're working through today.
Well,
Now hold that thought, hold that thought. And this is why I'm talking about. There's 1,000 different trials here, but each of the samples is only of size 4. So check it out. That sample right there has an average of 4. How close is 4 to the true average of the population? The average of the population is 8.2. The range of data is 2 to 12. How close is 4? Not very. Really? 7.25? 7.75? 8? 9.75? 6? 4.75?
so it has to do with 4 compared to the 8 rather than
So
1,000 compared
what
to
we
4,000?
see here, thank you Kate, yes. What we see here is, yes, the bell curve occurs, yes? But here's the catch. This is 1,000 different studies, correct? This is 1,000 different studies. Psychologists, statisticians, natural resource folks, you do one study at a time. One study at a time. Which means you're not going to get this entire graph. You're going to get one of those averages. And your average is going to fall somewhere on this curve. But the kicker is, your average might be as small as one of these 2.25s down here. It's not very likely. It's pretty unlikely, actually. Or it might be as high as this 11.25 over here. Not very likely, but still can happen. It's most likely going to land close to the average, which we want, but you still run that chance of falling in the tails. So can we fix that? Can we make it less likely to fall in the tails? Think about what Hattie said earlier. Can we make it less likely to fall in the tails? How, Hattie?
Just do it over and over.
Do more samples! So, next tab. This is what a sample of 9 would look like. I didn't make you guys do this yesterday. You rolled your dice 4 times and averaged them, right? This is rolling up 9 times and you might be asking why 9. We'll come back to that momentarily. So now, look. Let's F9 a few times. What are you noticing? What are you noticing? Stood at the bell shape, right? Stood at the bell shape. Now, an interesting thing happens because of the way the data is now grouped up. This guy doesn't pop up as much as this guy. That's just that's a little curiosity in how I broke the data up in Excel. Don't worry too much about that. I have a fix for that later. So we got a bell curve, yes? The high point is essentially still where the average is. But what happened to the bell curve?
Looks like it tightened up.
It tightened up like this, yes? Now, if it tightens up like this, where else does it have to go? Doesn't it have to go up? Why?
You still have the same amount of data.
You still have to make the area 100%. I don't know if you guys caught this, I'm a total bastard. I changed the distribution to a probability distribution. So instead of frequency, it's divided by 36 essentially. So you're looking at that. Oh, I'm such a jerk. So the area under the curve, instead of summing to 36 or whatever number we need, now has to sum to 100%. If you bring the curve in like this, it has to pop. It's like a Play-Doh. If you smush the Play-Doh here, it's got to go somewhere. In this case, it has to go up because it can't go down. Makes sense. Why does JC go? Go ahead. No, go.
Is this the precision that you were talking about with a bigger sample?
Thank you, friend. It's exactly what it is. Your precision is getting better. Yes. As you squish in, your precision gets better. Did you notice how we were getting like 2s and 3s and whatnot in the previous sample of size 4? Do you see them now? Every once in a blue moon, you'll see somebody pop up like right in here. But what you don't see are these wicked extremes over here or these wicked extremes over here. Because it's just mathematically too hard to get them now. In order to get down there, you have to roll 2 9 times. That's 136 to the 9th power. That's almost impossible. But we can do even better, can't we? Let's go to 16. Watch this curve. Now look at 16. Look at that curve. What do you notice? What's happening? How is it the same as the previous? Still bell-shaped. How else is it the same? The average is still the highest point, yes? How is it different? It's tightened down even more, yes? It's tightened down even more. Check out 25. So in other words, if it's getting tighter, what's changing in the actual graph? The average is staying the same, yes? So what's changing?
The variability.
This variability is changing, it's minimizing. Yes, we see it now. Look, look, look. The tails are vanishing. And when we get up to 100, which we do right here, this looks a little ridiculous. And a student asked me in the other class, she's like, that's not even a bell curve anymore. And I realized it is. But because the bins are so wide now, you can't see it. So last night, I went home and made this one. Now, this might be tricky to look at, but look at the horizontal axis. The distances on the previous ones were a half unit apart, 4.5 to 5, 5 to 5.5. These are a tenth apart. So all this data right here, FYI, all this data right here is between 7 and 9.5, which means this entire graph lives between here and here. So if you took this and literally chopped off those tails, which aren't going to happen probabilistically, chop off 7 and down and chop off 9.5 and up and stress it out and subdivide it up, it ends up looking like this. And how gorgeous is that? I know, Robert. You have to just stretch it. It's beautiful. But notice, even though I pulled the scale and made it more detailed, what's the same? Still a bell shape. It's actually a gorgeous bell shape. And what else is the same? The average is getting close. Now you're going to see it bounce around a little bit more. 8.166666 is actually over here. Because these are now broken up so finely, it's going to bounce, it's going to pop back and forth quite a bit compared to the other ones. But nonetheless, what you're never seeing is something that looks like this. Because you could probabilistically see it. What's the chance of it happening? Essentially 0. Because that would mean you'd have to get a whole buttload of outliers to happen. And that's like the anti-definition of an outlier. If you have a whole buttload of outliers, you can't call them outliers anymore. You have to call them, that's normal. And everything else is weird, right? That kind of makes sense? Now, let's regroup. As the sample sizes have gotten larger, okay, the bell curve's maintained. What else maintained? Say that again. The average stayed at the highest point of the bell curve. And how did the precision tie in, JC, again?
Because the sample size is larger, so it is shrinking.
Nice.
And then rising.
Perfect. And I want to go with one more exploration. One more exploration. Check this out. What I've done here is a little bit of a headache. I wanted to go up to a sample size of 10,000. I wanted to go to a sample size of 10,000. But the problem with that one was when I pressed F9, Excel was like, and then like 6 or 7 seconds later it would go like, and like put a graph, and I'm like, that'll bore them. So I think we can see what we need to see with the ones we already have. This is all 5 different samples on one graph. So this is a sample size of 4, 9, 16, 25, and 100. Okay, and if I press F9, you'll see them, they'll constantly update based on the new data that's back in the sheet. Okay? Statisticians tell you never to put stacked histograms like this. And I say, no, it's the perfect place for them. It's the perfect place for them, because now, don't you see everything that we just discussed? Every bell curve. But what, go ahead, Skylar, or Natalie, whoever that was. What do you know? What else do you notice? Go ahead.
And the average too is still.
It's right there in the line, isn't it? The average is right there in that line. The highest bar on average is always that guy right in the middle between 8 and 8.5. There's a little bit of fluctuation. Right now, that guy's a little higher than that guy. But on average, and what's happening as we move front to back? The curves are getting tighter and taller. Perfect. I want to go one step further, just one step further. We can tighten down how much tighter they're getting. It's actually quantifiable. And this is important because, here's why. Gallup, if you ever look at a Gallup poll, they'll say something like, we interviewed 1,200 Americans and asked them, do you approve of Congress? That's a stupid question because nobody approves of Congress right now. But they asked the question, yes or no, do you approve of Congress? And have you ever asked yourself, why did they choose 1,200 Americans? Why 1,200? Why not like 10% of Americans or 5% of
That
Americans?
makes their graph pretty.
You say that again?
It makes their graph pretty.
It makes their graph pretty enough. A 10% of Americans will make it even better. It would basically make this curve be a straight line straight up. There would be almost no variation in the graph at all. But Gallup knows how expensive it would be to do that. There's a ridiculous non-response rate on polls. You guys ever get junk mail that asks you to fill out like a questionnaire or a registration and then mail it back in? And who does that? I used to back in the day. Patty, question, comment? Question.
So, based on this, and I think
Yes.
this was a question that we asked like the first week of class.
Maybe?
So if you ask 1,200 out of 315 million Americans, that's like 3.8 to the -6th power.
Exactly. 0.00000.
So how is that a good representation?
You take 244, right?
No.
What the hell?
Exactly.
So what I'm getting at here, I have a question for your question. Hattie asks, how could it possibly be, with a tiny percentage of Americans, how's it a good representation? My question for you is, okay, we know congressional approval rate is out there somewhere. Just like Obama's approval rating, just like the number of people in Bend that approve of the surface water project, whatever it is now. The number of people in Bend that approve of the dam getting broken down and leaving Mirror Pond, not Mirror Pond, but whatever river it is. How off do you want to be in your sample? Because we know it's going to be off, right, JC? We know it's going to be off a little bit. What's the maximum percentage allowable you would allow it to be off? Percentage-wise.
Personally,
Personally, yeah.
maybe plus or minus 3%.
Perfect. That's pretty standard, actually. 3% is almost standard. How confident do you want to be in your result? Because you know you can always miss. We're not missing very much here, but every once in a while, remember how the bars pop up in the wrong place? How confident do you want to be? Between 0 and 100, you can't be 100% confident because of that. So,
95?
95%, that's pretty standard too. 95% confidence, 3% margin of error, you need 1,068 people, and that's it. Boom. That's it. The reason I say, you take a 244, I'll prove it to you mathematically next term.
But is that based on the
That's
current
based
population?
on your choice of 3% and 95%. It has nothing to do with how big the population is. If your population is less than 1,068, which sometimes it is, you just have to ask them all. And then you have a census, and you can throw statistics out the window and go, I got the parameter, I'm done. But if you've got a large population, it doesn't matter how big. If it's 10,000, a million, 300 million, 7.2 billion, whatever the hell number of human beings there are right now. 1,068 gets you 95% confidence and 3% margin of error. Isn't that wild? Now, if you ask more, your margin of error is going to shrink down. And you'll get even closer to what you're looking for, on average.
Is that why on the projects it doesn't matter how big our population is?
It's irrelevant. It's completely irrelevant.
I kept hitting my head against the
Mind-boggling,
wall, and Jackson
yeah.
was like, it doesn't matter.
It does not matter. It does not matter. And mathematically, we'll see why. I won't do it to you in 5 minutes or even an hour in 5 minutes. But in 244, we can set up experiments to actually prove to you why. Why you should care, first of all, and why it actually are those two values. So Hattie, don't worry yourself. 1,000 is fine. And now, you could actually survey like 6 people, as long as you can accept like a 20% margin of error. I'm fairly confident that between 10% and 90% of Americans dislike Congress. I mean, if you could say that, and that's statistically true, it's also useless. It's also useless, yeah? So, remember the joke I started with between the 7.6 and the 7.8%? That could be statistically significant if you have a large enough sample, because your margin of error will shrink down so tiny that there might be a difference between 7.6 and 7.8%, because they won't overlap each other anymore. Does that kind of make sense? Ish. But we'll explore that road in much greater detail. It's based on this road, though. This is the road that takes us to there. So as your sample sizes go up, they get tighter and tighter and tighter. And you can imagine at some point, this will be one single bar going. That's what I was trying to get 10,000 for. Because if I could get to 10,000, it would be one single bar. It's essentially 100%. I mean, granted, if I then microanalyze like I did with 100, it would break out into a bell curve, but a very, very tight, tall bell curve. Now, what was the question that started that discussion, which is fantastic, by the way? I was going somewhere else, and that got it derailed in a perfect way, not in a bad way. I don't know, we'll come back to it. So remember this. That's what the population has that we'll never know, yes? We'll never know those. This is giving us a pretty good idea, though, of where at least the middle is. Good. Now, what I want you to do is I want you to watch these right here. Those are, I call those the average of all the X bars. Remember how I ran 1,000 trials in each sheet? So a sample size of 4, we had 1,000 of those. A sample size of 9, we had 1,000 of those. This is the average of all of those averages. So each of those averages, 4, 7.5, 7.25, look what's happening on average as I keep rolling the dice. Now you knew this was going to happen. What are all those numbers doing?
Fluctuating.
They're fluctuating, but not too far from what? Not too far from average. Yet from mu average, right? From mu average. Oops. Not too far from mu average. So that's good. Good, Andrew. That's good, right? That's what we want to happen. That ties into JC's curves that are getting taller, but still lining up on that 8 to 8.5 bar. That's perfect. Check out now I did the same thing without just the averages though. I took the standard deviations in the samples. So in other words, each of those samples has a standard deviation as well. The sample of size 4, the sample of size 9. This is the average of all the standard deviations in those 4, 9, 16, 25. What's happening as sample size gets larger? Clearly getting smaller, right? But now here's my question for you. Is it getting smaller predictably? For example, if I were able to have created the n equals 10,000 sample, what would this be over here? Ish.
0, 0.
Give me more precision. More precision. My vote, it would be somewhere in the neighborhood of 0.027. Now, I can't do it because I'm going to freeze Excel. But I can prove to you, I think, you can figure it out right now. What's this number here? Ish. Compared to this number over here. Ish.
Half.
I gotta vote for half? Is it half a good estimate? Okay, I'll put that over here. Excel. Hang on, how do I do the format cells number? Oh, I just freeze it? Oh, there we go. Number. Okay. Oh, what the hell is that? Format cells. General, maybe. You know what? To hell with you. 0.5. Boom. Okay. What's this one? Ish. Compared to this one. Ish.
A third?
Be brave. About a third? I think that's about 0.9. That's about 2.7. That's about a third, isn't it?
Yeah.
Ish. Yeah. How about this one here? Looks like it's hovering around like 66 or 67 hundredths. Roughly.
A quarter maybe.
About a quarter-ish. About a quarter. Oh, you know what we can do? You know what? Let's be smarter about this. Let me do equals 2.69 divided by this number. There. That's about 2, isn't it? Oh, you know what? Let me do it your way. Let's do equals this number divided by 2.69. That way you keep the fractions. So there's your 0.5, yes? Okay, we drag it down. You guys said this was about a third, yes? Yeah, looks like it's about a third. You guys were calling this one about a quarter here? Look at that. Hot damn. How about this one? What do you think? 0.5 versus 2-ish? Ish a fifth? Ish a fifth? Let's drag it down, take a look. That's damn close to a fifth. How about this one here? About a tenth. Ah, I was a bastard. I slid 100 in there, didn't I? Jerk. That's about a tenth, isn't it? 2.26 to 2.6. Drag it down. Notice what's happening. Those aren't changing too far. Do you see any relationship mathematically between these numbers and some other numbers up there? So you might have asked yourself, why the hell is he doing sample sizes of 4 and 9 and 16 and 25? And then he does 100, and then he mentions 10,000. Why would he be using those numbers?
Perfect squares.
Because they're perfect squares. And how are perfect squares related to these? You guys said that was a half, yes? And this is 1/3, 1/4, 1/5, 1/10. You see it, Andrew? Let's hear it.
Yeah, so it's half of big 4 divided by a half is 2.
If I do 1 divided by the square root of the sample size, and drag that SOB down, look at those numbers. And look what they're averaging. So why was I going to go with 10,000? What's the square root of 10,000? 100. Just take a couple of zeros away, right? And if it's 100, that means I could just look at that and move this bad boy 2 spaces over and call it 0.0027. That's why I predicted it's going to be 0.0027. Michael, when you said 0.027, when you said basically 000, I said more precision. Because it wouldn't be that low at 10,000. It would be off by 1 extra 0 from 100. And that's the interesting thing about sample sizes. You have to quadratically increase them to pick up 1 decimal place in precision. So this is what's cool. Yes, JC, it's shrinking like this, and the curve's getting taller like this. But it's shrinking predictably. Yes. And that's the whole point of today's wrap-up. That is the whole point of today's wrap-up. You don't have to write this down, of course, because it's posted for you. This is already posted from last class. I'm going to post it again today. Let's summarize. Put it all in 6 easy steps, easy to digest steps that you can use on your take-home exam. This is the whole point of statistics. This is why you do it. You're studying a population, whether it's children with ADHD, whether it's American voters over age 24, whether it's the weights of pregnant women in their 3rd trimester. Whatever you're interested in studying, you've got a population. And that population, whatever characteristic you're studying of it has an average. And are you ever going to know what that average is? Most likely. In your population. That's the whole point. That's why the class is called statistics. It's not called parameters. If it was called parameters, this would be a boring class. I would say, yes, good morning, my name is Sean, this is Matthew 43. Your lesson for the next 10 weeks is go out and count everything forever. Goodbye, we'll see you at the final. And that's what parameters would sound like. Go count everything and then come back with a number. But you can't do that. You can't do that. So you draw a sample, and it's usually, I'm going to call it of size n. Because n is usually a variable quantity. You have to pick n depending on how confident you want to be in certain things. Back to your 95% confidence value. So it's got an average, it's got a standard deviation, neither of which you're going to know. The best you can do is grab a sample and study your sample. Now we just learned some valuable information about that sample, didn't we? What's going to happen with that sample data? It's going to fit onto a what? Boom! Number 1. Fits on a bell curve. That makes us happy. Yes, it fits on a bell. It itself doesn't. It itself is not a bell curve, but it fits onto a bell curve. So make sure you make that connection. It fits onto a bell curve. It itself, the data itself might not be perfectly bell-shaped, but it itself is one component of a bell curve, of which you only get one teeny snapshot. We'll deal with that. We'll deal with that though, Megan. So that's our first yay. The second yay is that the bell curve, yes, yay squared, because that means although there's going to be variability in our sample, it's most likely that we land close to mu. This makes us happy. Why?
Because you can apply it to the population.
Yes! Because that's what you're studying, JC. You can apply what you've got and say, damn, I'm probably pretty close to mu. Now, I made up a symbol here. I hope that doesn't matter. We're going to talk about unbiased estimators in 244. Don't sweat that too much. X bar would be your sample average from your data. X bar is your sample average, your data. X double bar I made up to indicate all possible sample averages averaged together. So I was kind of doing that in the spreadsheet where I had 1,000 of them, and then I averaged all 1,000 averages in that last sheet. This is making a lot of you sick, I apologize. So the problem is you get X bar, but if you were to average all the X bars, yes, on average, all the X bars average to exactly mu. And I can't emphasize this enough. That is an equal sign. That's not a squiggly equals, that's not an ish. That's an equal sign. On average, it will be mu. We'll talk more about this in 244, I promise, those of you going on that journey. Because that's not good enough to just leave that. That's like hand waving, like, oh, magic, mu. No, it's not magic, it's algebra and it's mathematics. But on average, the X bars are going to average to mu. Is your X bar going to equal mu? Exactly. No, it's not. And here's the problem. Step number 2. The problem, this is the only boo of the central limit theorem, is that your X bar doesn't equal mu. There's always going to be a slight difference. And I say slight in quotes. It might be a vast difference, as we saw. The average might be 8, and you come back with an average of -2. Hopefully not, because that would be an outlier data point. But it could happen, yes? Could happen with an outlier. This goes back to Hetty's 95% confidence. I'm throwing a lot of 244 things out, because this is kind of a bridge. It's like between, it's the two things between, or it's the one thing between the two courses. So what we do is we admit this fact. And what do we apply? To the average, which we should always technically apply to it. And we talk about this in week 3 in this course. You don't just look at the average of a data set, like with Bert and Ernie. What do we also look at? No, Bert and Ernie, since this is so long ago. The jokes were still funny then. Bert and Ernie also had a what that we could measure? Boom! And that's this beautiful, beautiful thing. This is yay 3. There is a new term I want to plant in your mind now. You'll probably forget it in 3 weeks when I see you again. It's okay. It's okay, man. It's okay. But it's called the standard error of the mean. It's given a new name. I think. I don't know the answer to this wholeheartedly. Your sample standard deviation, we always just call S. The problem with S is, S doesn't do anything except describe the standard deviation in your sample. That's all it does. It says, okay, here's your sample data. Here's how off your sample data is from the sample average. Yay, that's good. That's extraordinarily good. What the sampling error, or the standard error of the sampling distribution does is, it makes an adjustment. It makes an adjustment and says, okay, that standard deviation that you get in your sample, if I want to apply that to the entire population, you have to admit the fact that as you sample more data points, your error is going to be less because you're getting a larger chunk of the population. It's got to be shrinking. Now, this divided by root n might freak you guys out a little bit, but it shouldn't, should it? Because didn't you just discover that? Remember that? The 1 over 2, the 1 over 3, the 1 over 4, the 1 over 10. Andrew, you said, oh my God, wait a minute, if I take the square root of that and put it over 1, you discovered that. If you take sigma and do times 1 over root n, you get it. So what this means is, as n goes to infinity, your sample error goes to 0. That's a little bit of calculus for you first thing in the morning. As this gets larger, this gets smaller. And if you let that get large enough, JC is what I was talking about before with you. If you let this get large enough, this becomes almost negligible. That's why 7.6 and 7.8% could be different. If this is large enough and that's small enough. And again, we'll talk more about that at great depth in 244, I promise you.